So please make sure that you are really getting along with the class materials. And if there is a problem, please raise your voice. This is the time to speak up. If you do not speak up, I'll just keep going on, and you will lose track. Go ahead.
There was one problem that was, it was one of the pole problems where it was like the lines are separated very far. Then what would happen? And the correct answer was they would easily discharge. But the correct answer should have been that the material cost would be too high because of how, so that the wrong answer was.
I see.
Was the right answer.
So the right answer was there, but
yeah.
incorrectly labeled as wrong answer. Okay, so thank you for bringing that to my attention.
There were several of them that were worded almost ambiguously. It made kind of like, it felt like there was some room for interpretation on a few of them, where you could argue that there are two best choices for some of them. The one that I'm thinking of specifically is the one where the finite length wire is much longer than the distance between the charge. But if you were to, I forget if it was increase or decrease the separation by 2, what would happen to the field? And there was one that it would increase or decrease by a factor of 2 because it's proportional to 1 over d. But then there was also a choice of it would almost be the same. And that's what I put, and it was counted wrong. But I would argue that's close enough to true because we talked about the scale.
Understood. I understand.
So I don't mean to argue for points in front of that.
No, I think I got your point. So what you are driving at is that because these questions are more verbose than mathematical, then there are rooms of interpretations. And it might be possible that some of the answers are very close to each other. So it might feel more fair if you are given a credit for an answer that is somewhat true, or that can be interpreted to be very true. I understand. That's actually a very valid point. So let me think that maybe from the next exam, instead of having a multiple choice question, I'll have an option to choose the best possible answer. And maybe you will have some credit for those interpretations. But remember that we will try to avoid those interpretations because those are very personal choice. Somebody else may think that, no, this is not the way to think at. We have to think in some different way. And the other problem of having a word-based problem is it's always human-based interpretation. So I'm still trying to navigate at which one is the best possible way to judge people. Okay, I apologize for this inconvenience. Maybe it's not only just a word problem, but maybe if I bring some little bit of math, it will be less controversial. So we'll experiment through it. Okay, and thank you for bringing this in attention. And yes, go ahead.
So, not for the quizzes, but for the actual exams, is it going to be like the quizzes, more theory-based?
So, in the actual exam, that means in the mid-exam and the final exam, it would be a combination of your quizzes and your homework. So, did you guys notice that your homework is mostly based on mathematics? Your class quiz is mostly based on word programs, stuff that we discuss in the classroom. So we do the combination of both of them. Yes.
So if we have a problem with one of the homework questions, like, can we ask you about that?
Of course.
Can we go over?
Go ahead. This is the time.
It was the one where you had to solve for the angle, and in the book they use like the matrix equations to solve the angle.
Mm-hmm.
But no matter what I did, I could not get one of your answer choices. Like, I tried so many ways. I probably worked like...
Number 3 on homework 1. Okay. We couldn't solve for the theta hat value. We had to kind of make a best guess thing. That's...
Okay. So I don't remember just what was the question, but is it something like a problem? That we have a coordinate system, and we're trying to find out the point, and if we draw a vector along that point, what is its representation in Cartesian coordinate and what is its representation in the polar coordinate. Right? So probably that was the question, and you were asked to convert these vectors from Cartesian coordinate to polar coordinate. Was that something like this? Yeah.
I have a question.
Can I see it?
Would you be opposed to like posting written out solutions to the homework, or is that just not something that you would do?
Yeah, let us work on that. That's a good suggestion actually. So I will work with my TA to see that if we can post a written solution so that you can see that how the process goes.
Obviously after it's due.
Sure. But I think the first homework is, the due date of the first homework is September 6th. Is that correct?
Yeah.
So we are yet to get there, right? Oh, that means I cannot talk about it.
Yeah, I didn't notice that after we asked, sorry.
All right, so let me give you a clue, okay? I mean, I'm not going to review the answer, but let me give you a clue. In a Cartesian coordinate, we express any vectors in terms of x hat and y hat, right? In polar coordinate, we try to express a vector in terms of r hat and theta hat. Okay? And how r hat and theta hat is defined? R hat is directly drawn from the origin to the point of interest. Okay, so if P is the point, then r hat will always be directed this way. Okay? If P is here, then r hat will always be in this direction. Right? And theta hat is always perpendicular to r hat. So the angle between theta hat and r hat is always 90 degrees. All right? So based on what I drew here, this is 45 degree angle. This is the point P. It has only x hat and y hat component of equal magnitude. And if I try to convert this thing into polar coordinate, what would be the value? I'm not going to write it, but I'm just giving you a clue. Should it have an r component or not? It should have an r component, right? I discussed that r hat is directed from origin to the point P. So clearly, these guys have an r component. So it should have an r component, and maybe it has some coefficient that you have to figure out. And let's see how much component it has for the theta, phi hat. Let me just write it phi hat. So what do you think? This vector and phi vector, they are perpendicular to each other. So if I ask you that what is the component of this vector along phi direction, what would be your answer? Let me write it again. Let me ask you a different question. If I ask you this, we have x and y coordinate, and we can draw x hat and y hat vectors. If I ask you what is the component of x hat vector along y direction, what would be your answer?
0.
Right? Because they are perpendicular. So try to implement the same concept here, and you get your answer. Okay? And choose the closest possible answer. Closest possible answer. So yesterday we discussed about a relatively new concept, divergence, and I told that divergence can be thought of as a source of water and a sink of water. If it's a source of water, then the divergence is positive. If it's a sink, then divergence is negative. And I showed you some diagrams of vector fields. And looking at those diagrams, you might be able to tell whether we have a positive divergence or negative divergence. Right? For instance, in our very well-known expression of Coulomb's law, we write electric field is proportional to kq by g squared. Right? And it always is pointed towards the vector r hat. How? Let's say we have a point source with a q plus charge, and we are trying to find out this corresponding electric field at a point p, arbitrary point p. So this would be the r hat vector, and r hat vector makes an angle theta with x and y coordinates, right? So we can always write this vector into x hat and y hat terms. We just multiply x hat and y hat with sine theta and cosine theta. And this cosine theta can be converted back to x and y values by the following way. Cosine theta means x divided by root over of x square plus y square, and sine theta means y divided by root over x square plus y square with the y hat vector. And this d square, this guy, d square is basically the summation of x square and y square. Okay? So once you put back all these things, you can draw the corresponding vector diagrams. How this vector diagram would look like? If this is the point at the origin where we have q plus charge, and if you try to draw these vectors, it would look like radial. Okay? And the farther you go, the weaker the electric field would become. Okay? So we know that if we take the derivative of it and find the divergence, we will see that the divergence is zero everywhere except at the origin. Okay? Except at the origin, the divergence is zero everywhere else. Okay? And that's how we know that since the divergence is non-zero at the origin, that means there must be some sources or sinks at that origin. If the value of the divergence is positive, that means it's a positive source. If it is negative, that means it's a negative charge. Alright? And we also looked into some other shape of vector field. For instance, I tried to draw electric field which may look like the following. Let's say electric field is this. E equal to x hat. That means E is directed towards the x-axis, and it has a component corresponding to the coordinate value of x. So this means if I have a coordinate system x and y, then how should I draw this electric field? At the very origin, the value of electric field is 0. Why? Because x is 0 at the origin, right? But as you go to the right direction, this value of x is going to increase. So that means the farther you go towards your right, these arrows must be increasing in terms of length, right? And they are all pointing to the x hat directions. What if you go upward? If you go upward, that means you are going to increase the value of y without changing the value of x. If you just change the value of y by going upward, no impact would be there for the value of e, right? Because e doesn't depend on x. So this means if you just keep going upward, you should not see any change . And similarly, on the other side, you would have vectors that look like the following. does this vector field, if it is represented by a water flow, do you think that those water flow have some sources or sinks, or it has no source or sink? This water flow indicates what is the velocities of the waters at a point. So let's look at one point here. It says we're having some water, and we're having some water out of this point. The small arrow says that water flow is little, and the big arrow says that water flow, the water velocity is high. So this point must have some water source, right? Do you follow? If it has no water source, then all the arrows, pointing arrows, should be equal in their magnitude. So in this field, we must have water source at every point, every possible points. Okay? So if you take the derivative with respect to x, that means if you try to find out the divergence of electric field, you have to calculate dx with respect to dx, dy with respect to dy, and dz with respect to dz. And all these other components will be 0 because we have no x and y and z components. We only have x components. And if you take the x component, take the derivative with respect to x, you will get 1. So this means, 1 means, no matter what is the value of x, you will always have a source with a strength of 1. Okay? You will always have a source with a strength of 1. What if E is x squared? If it is x squared, that means the further you go to the right, the bigger the value of arrow would become, right? So these arrows, as you go further and further right, they would start to increase at a higher rate, right? All of these guys. These arrows would keep increasing at a faster rate. So what does this mean? If you are given a diagram like this, you should assume, you should understand that maybe these have even higher strength of water source. They're spilling out of water much more faster. So in that case, you take the divergence of E, which is the divergence of x squared with an x hat, which will be yx, right? So it says previously we only had a divergence of 1, and now we have a divergence of 2yx. So this means as you go further to your right, the x value will increase, and correspondingly the value of divergence will increase. So we have more water source, stronger water source, and for this corner. Okay? Previously you had similar strength of water source everywhere, and now you change the scenario. Are you following? Everyone? Okay. We also talked about a new kind of relation between divergence and its integral form. We say that if you have a box and you're going to calculate the divergence at each of these points in order to find out whether there is a net flow of water or net outflow of water, you can do the following. You can take divergence at each of these points and take the integral over the entire volume. And interestingly, the result will be exactly same if you just take the water velocities only at the surface of this box, not looking what is going on inside. So these two guys are exactly same with each other. And this is called the divergence law of Gauss. Have you heard the name of Gauss previously? In which context?
Electromagnetics.
Okay. So Gauss was a mathematician. If you have taken a course on mathematics, you might have heard his name also. Okay? Like Gauss was a Carl Friedrich Gauss. He was a prodigy. From the very earlyhood, he showed his genius. And there is an interesting story which says that when Gauss was at his earlyhood, one of his class teachers, he gave them, the entire class, an exercise just to keep them busy. So he said that you guys count up from 1 to 100 and add all of them together and find out the answer. Okay? So basically, he just asked the entire class to find out the summation of all these guys up to 100. And it was a very early class, and the class teacher thought that maybe it will take the entire time for all of them to find out. It's not easy. And meanwhile, he will do his own job. To his surprise, that one guy, he stood up and he said that, I'm done. And he showed his work. And the way he did it is very simple. He just reversed all these numbers. You know, it's like this: 100, 99, 98, all the way up to 1. And then he added up all these lines. So it would be 101. It would be again 101. Right? It would be again 101. So how many 101 we will get? How many 101? 50. How many digits are here? 100, right? So we will get 100 101. So that means the summation is going to be 101 multiplied by 100, but you counted everything twice. So you took half of it. And he said, that's the answer. And that boy was Gauss, Carl Friedrich Gauss. Okay? So he showed his genius at a very early age. Anyway, so when Gauss gave this discovery of divergence, he didn't know anything about charges. Charges was discovered much later. But he said that the mathematical function of a divergence should have this form. The divergence and the integral of this divergence over an entire volume should be equal to the velocity vector integrated over a surface. Okay? So we utilize this function in electromagnetics a lot. So today we will see one of those examples, like how we are going to utilize the Gauss Law, and we might be able to find the solution of some problem that otherwise takes a lot of time. So one very important formula for electromagnetics is the following: that the divergence of the displacement vector or the electric flux is proportional to the charge density. Let me write it all the way. So this is charge density. This is electric flux, and this is the divergence output. Okay? So this means if I take the derivative, if I take the integral of this relation, we will get the following: the divergence of D over the entire volume is equal to the integral of the charge density over the entire volume. Okay? Now look at that. Charge density means how much charge is there per unit volume. So if I take the integral of charge density with respect to the volume, I will get the total charge. So this is actually the total charge. And Gauss law says that the divergence and its integral is actually same if you take just the vector itself and integrate the vector over the surface. You will get the same value. So the divergence, instead of divergence, I'm just using the vector itself. I took the integral of the vector over the entire surface instead of the volume, and I get the total amount of charge. Okay? And how it is going to be interpreted? Let's say I have a plane, and we have a charge somewhere, and if we draw a box around that charge, then calculate all the electric fields that is coming out of this box, and take the integral of all this electric field along the surface. Thus, that integral would correspond to the magnitude of the charge. Okay? Let me tell you one more time. It might be getting a little bit complex. So, we're saying the following. If we have a charge somewhere, if we draw a box around that charge, any size of box, okay? Any size of box. It could be a bigger box also. So once we draw a bigger box or smaller box around that charge, and we try to see how much electric field is coming out of that box, we take the integral of all this electric field around the surface of that box, we will get a value which will be exactly equal to the charge inside that box. Okay? So, if there is no charge, if we draw a box, you will still have electric field, right? You have a charge here. You don't have any charge here, right? Inside this box. But we have electric fields that's going in all different directions. Right? So we have some electric fields also that is coming inside the box and leaving the box. But if you take the integral of electric field around the surface of this box, the value that you get is 0. Because inside that box there is no charge. And why is true? Let's look at this. All the electric field that enters the box is equal to the same electric field that goes out of this box. Okay? So if you take the integration of all the electric field, you will see that it's equal number of electric field that enters the box, and it's equal number of electric field that goes out of this box. That's why when you integrate all of them together, the summation will be 0. Okay? I can also say this because I know that inside this box there is no charge. Alright? Is it getting very complex? So the bottom line is, if you have charges, if you draw a box around it, the total electric field integrated over the entire box surface would be non-zero. If you do not have any charge inside the box, then the integral of the entire electric field around the box would be 0. Okay? So integration tells you what is happening inside that box. A zero integral means that there is no charge inside. A non-zero integral means there must be some charge inside that box. A positive value means there is a positive charge. A negative value of integral means there is a negative charge inside that box. Okay?
We're talking about the integral of the flux, right?
Integral of the flux.
Okay.
You can also say that it's an integral of the field, because in typical case, in a very typical case, the flux and the field is just a scale factor of each other. Okay? So if you have a field, you just multiply it with a constant value, you'll get the flux.
Right. Okay.
Okay? in later period, when you will, in advanced class, you might notice that this guy, this epsilon, is not actually that simple. It could be very complex. Okay. Maybe your entire life would be spent just to find out what is epsilon of a particular medium and how differently it behaves. For now, it's absolutely okay just to think that epsilon is a constant term. Okay? Just to make our life easy. So let us see if I try to utilize these particular equations and try to solve one of the previous problems that is solved in a different way. We solved the electric field owing to a very long electric wire carrying a charge density rho. Right? Let's say that we have this length twice, which is very, very long, so I'll consider it infinite. And I'll try to calculate electric field at a distance d from that charge, from that wire. Okay? So previously we did the following. We took each of these segments and we calculated the vector fields for each of these segments, and then we integrated over the entire wire length. And then we got some value. We found that the total electric field will be directed along the x direction if it is y with some magnitude. Right? So today we will try to utilize this guy, and see if we can solve this problem without invoking any vector addition program. So for a long wire, you already know that all this electric field must be radially outwards from that wire. Right? If I have a long wire, all this electric field will be in those directions. Right? So what Gauss does is the following. According to Gauss law, we can actually draw a cylindrical box. Let's say we want to find out the electric field at a point P. And from the argument of symmetry, we know that this electric field must be radially outward from that long wire. So what we did is that we took a cylinder in such a way so that the radius of the cylinder is equal to the value of d. D is actually the distance from the wire to that point P. Okay? And what is the height of that cylinder? Arbitrary. You just take any height, not a problem. Let's say we take a height of h. Alright? So now let's see. This guy says if you integrate the electric flux over the entire surface, you are going to get the value of charge inside that box. So now my box is cylinder. I know that my electric field is only radially pointing outwards, right? So there is electric field. If I have these long wire, all my electric fields are going to be directed in the radial directions, right? There is no electric field in the y direction or in the downward direction, right? All the fields are in the radial direction. So, since I drew a cylinder has three surfaces. One is at the top, one is at the bottom, and one is around it, right? So, in the top surface, we know that there is no electric field that is pointing outward, right? There is no electric field pointing upward. So we can easily say that if you integrate electric field on this surface and on the bottom surface, you would get the value 0, right? So we can safely ignore the integral on the top and on the bottom plate. We know that the integral would only have some non-zero value if we go around the cylinder. So we can easily write that the integral of electric field over the entire surface would be the following. Electric field would be constant around this entire surface because the distance is always same, right? So we can take electric field out of these integral relations. What we are left with is only the integral of the surface. And I know that the surface of this cylinder is simply 2 pi d multiplied by h. And then we multiply with electric field. So this is the area of the cylinder. Okay? This is the area of the cylinder. If we take a cylinder which has a height of h, which has a radius of d, this will be its corresponding area. And we multiply it with E. Why? Because we know that no matter where we are on this surface, the electric field will be constant if you go around this cylinder. So let's just use Gauss Law. Gauss Law says that this guy is going to be equal to the charge Q that is inside that wire. Now we know that this wire has a charge density of rho. So that means if you draw a cylinder which has a height of h, this guy Q is going to be a multiplication of the charge density and the height of this cylinder box. So eventually we get this. So if you solve for this guy, you see that electric field is simply rho divided by 2 pi d. Actually, I think I made a mistake here. So let's just include the factor epsilon. Okay? Remember that it's actually d, not e, and d is related to e by a multiplication factor of epsilon. Okay? So that would be the final expression of electric field for a long electrical wire having a charge density of rho. Okay? So if you compare this result with your previous class notes, you will see that in previously we did vector additions, but we eventually arrived at the same conclusions. Okay? If we use the Gauss law, our life becomes easy in some of the cases. Okay? We will just use a few lines of argument and we will get to our result. Okay? So one important point here, yes, go ahead.
Just a quick question. For our sake of calculation, will we always be given epsilon as a constant value?
Yes,
Okay.
always. At least for this class, we will always be given epsilon as constant. Okay, but just for your understanding, please remember that epsilon could be very complex, right? It could be dependent on frequency, it could be dependent on the directions, whether we are working the x direction or y directions, epsilon could be very different. But for usual cases, epsilon is constant. Okay, so one important note here is that when we integrate d over the entire surface, remember that d is a vector. Okay? D is a vector. And we take the dot product of d with respect to the surface. So surface is also a vector. Now you can question that how come surface is a vector? Surface is a scalar number. Hang on a second. We can also define surface as a vector if we say, for instance, in this cylinder, if we draw a small box, a small surface on the cylinder, we can say that the direction of the surface is actually perpendicular to the surface. So if we draw a surface on this plane, then the direction of the surface would be perpendicularly outward. Okay? This would be the direction of the surface. Okay? And why the surface all of a sudden surface became vector? It's only a mathematical convenience. Okay? Only a mathematical convenience. I think we previously, in previous class, you may have heard of the scalar quantity and vector quantities, right? And typically, in those early class, people defined scalar quantity as something that has only magnitude, and vector quantity is something that has magnitude and directions, right? In advanced class, the class where you are right now, you should understand by this time that these are all mathematical convenience. Okay? I can take a quantity which is scalar, and I can make it vector. For instance, if I tell you length, is length a scalar quantity or a vector quantity? What would be your answer? Length is a scalar quantity. Okay. We talked about the current also, right? Voltage and current. Is voltage, current, are those scalar quantities or vector quantities? Is current a scalar quantity or a vector quantity? Vectors? Anybody else? Scalar? So maybe some people have a different opinion. Some people think that it's a scalar quantity or it's a vector quantity. So let us try to understand these things once and for all. Okay? If you design this room and your job is to do the electrical design of this power supply, and I ask you to take a wire around the corner and come back to this position, okay, to give the electrical power supply to this light. And what if, instead of following that direction, you follow some other direction? You take the wires on the other corner and come back here. Would it be a different power supply or same power supply? Same. If you change the direction of the wires, would it be same or different power supply? Same. You understand that? So the direction of the wires does not make a difference to your final output. You follow? So this is why we say that when you change the direction of the current, it doesn't matter. It gives you the same power. Right? Okay. Now tell me this. If I give you a wire and let's say this wire is carrying a current, and because of the current, it's creating some electric field at a point P. Alright? If instead of this direction, if I change the wire and make it go around this point, would you get the same electric field? Yes? Let me tell one more time. I'm trying to find out the electric field for a wire. Okay? And one guy made the wire just long, and another guy took the wire, moved it around the point. Would I have the same impact? No. So we are seeing two different cases. In one case, we have seen that if you take a wire, move it around the corner, we'll get the same power supply. Not a problem. In another case, we see that if we change the shape of this wire, we get a very different result. So it really is a context-dependent thing. This problem is totally context-dependent. That means if you say that a current is a scalar quantity or vector quantity, you really have to specify that what context you are talking about. If you are talking about just supplying the power line, yes, sure, current does not matter. I mean, no matter in which direction current goes, we just care about whether the connections are there, coupled, right? But if you talk about the electric field, then yes, the direction of the current matters. So in one case, in the previous case of the power supply, the current can be treated as a scalar quantity. We don't care about its direction. But in the other case, when we are talking about the electric field, we of course do care about the direction of the current. So in the later case, current becomes a vector quantity. In the previous case, current was just a scalar quantity. Do you follow? So please always remember that whether a quantity is scalar or vector, it is really context dependent. Will you remember this?
Of course.
Okay. Thank you. So going back to our previous discussion, that a surface can be defined as a vector quantity. Okay? And how the direction is defined? The magnitude is defined very easily. You know that the surface is simply the multiplication of the length and the width. The direction of a surface is always radially pointing outwards, perpendicular to that surface. Okay? So if I have this board, I can calculate the surface of this plane, and the direction of that surface would be radially outward from that surface. Okay? So when we utilize the vector property of the surface, we can easily make a dot product with another vector quantity, and this is how we get the total result. Okay? G dot ds means we are taking the integral of electric flux over the surface. Okay? Let us look at one more example. Let us say that instead of having a wire, we have a wide plane of charges. Okay? A wide plane of charges. And let us say that this guy is y-axis and this guy is x-axis and this guy is z-axis. Alright? And we will try to find out the electric field at a point P, at a distance d from that sheet of charge. So tell me the following. If I have a sheet of charge, let's say that this is the sheet of charge, and I'm trying to calculate the electric field that is coming from this sheet of charge. What is your guess? What will be the direction of the electric field? You can consider this is a very large piece of sheet. Okay? I'm trying to calculate electric field at a position very close to this guy. What will be the direction of the electric field? What does your common sense say? I know that you have not done it.
Normal to the sheet.
Normal. So electric field could be in this way, right? These directions. It could be this way, or it could be totally perpendicular. Why do you think that it is perpendicular? There must be something is going on inside of here. So just spell it out.
The x components cancel. The positive and negative x component of the sheet cancel.
Very good. Very good. So the argument that you guys are presenting is that let's say I do not know what is the direction of the electric field. So let us say that the electric field is in these directions. Okay? But I do know Coulomb's law says that each of these part of this sheet is going to produce some electric field, right? Now, if this is a very long piece, very wide piece of sheet, then of course, if I go one position and try to calculate its impact, I must be able to find a mirror position which is creating an opposite impact. So if I have an electric field in these directions, I must have a mirror position which will create an electric field in the opposite directions. Right? So there must not be any field that is in plane with that sheet. This is why all the electric field, if there is any, it must be directed radially outward from the plane. Okay, this is really the argument. Thank you for this. I really appreciate that before going to math, you should have this common sense that what might be the direction of the electric field. It's very important characteristics of a successful engineer. Okay, you must always possess this kind of argument. Okay, and it comes from the symmetry. I know that even you cannot spell it out, there might be other people who can also tell that the electric field might be radially outward from the plane, but you may not spell it out that why you are saying it is upward. So the correct answer is that we have all the mirror components and they will cancel out the electric fields in plane directions. So we will only have perpendicular direction of electric fields. Okay? Does everyone follow? It's the same argument why when we say that a long piece of wire which is directed along the y-axis, it must have an electric field along the x-axis. Because all this y component, if this guy has a y component of electric field, this y component is going to be cancelled out by another mirror guy, because they are in exactly opposite position with a different directions. So all this y component is going to cancel out, only the x component will add up. In a similar way, instead of just a long piece of wire, now we have an infinite sheet of charge, and we can argue in a similar way that all these other y component and z component, they will go away. The only component of electric field that survives is the x component. Okay. This sheet is in the yz plane, so this is why all the electric field must be directed along the x-axis. Okay. That's the argument. Now, we only talked about the component directions, but we are yet to find out the magnitude of the electric field. So how are we going to find out the magnitude of electric field? One possible way is to just use Coulomb's law. And how we are going to use that? Let's say we are trying to find out electric field at this point. Let's say it is P equal to X, Y, Z point, and it is at a distance of G from the sheet of charge. So we can calculate the contributions of a very small segment of sheet and find out its impact on that small point. And then we will try to integrate over the entire surface. Okay? But instead of doing this kind of approach, we can use Gauss law. And let's see if Gauss law makes our life easier. So Gauss law says, if I draw a box, in such a way so that this box penetrates this surface, then we know that at the surface of the box we will have some electric field, and if we integrate the electric field over this entire surface of this box, we will get a value which is equal to the charge Q which is inside that box. Okay? And how we are going to utilize it? Let's see. So we know that if we draw a box, all this electric field would be along this direction, along the x-axis, right? All right. So we can simply write that epsilon electric of electric field multiplied by the surface of the box must be equal to the total charge inside that box. So we can take out the electric field of this integral equation because we know that electric field is going to be constant on this surface. Right? No matter where it goes, the electric field is the same because this sheet is infinite. So take electric field out of these integral equations, and inside the integral, we simply have the integral of the surface. Right? Now let's look at the integral of this surface. What is the area of this surface? In order to know the area, we just need to know what is the dimension of the boxes, right? So this box can be very arbitrary, okay? Very arbitrary. You can take however large you want. So if I take a box which has a dimension of, let's say, L and a width of W, then this answer is very simple. It's actually L multiplied by W. That's the area of the surface. Right? Now look closely. We are only considering only one surface of the box. How about the other surface? There are 6 surfaces of this box, right? What's going on this other surface? What is the direction of electric field on that other surface of this box? What is your common sense? Would it be in this direction or would it be in that direction? This direction, right? Yeah. Or this direction? negative x direction, right? They should be all symmetric. So if you have a plane of charge, like this plane, you should have electric field along this direction, and on the bottom, you have electric field in the other directions, right? But on the same directions. So, this other surface of this box must have an electric field pointing to the opposite directions. So what are you going to do? You multiply this entire term by 2. Why? Because the electric field changes its directions. What about the direction of the surface? This surface must also have a direction along here. Okay? So this integral and this integral, the surface integral, both of them have same values. That's why I multiply this entire stuff with a factor of 2. Anybody have a question? Okay. Now let's come to the other part. This is the easier part. We are trying, now we know that we drew a box which has a length of L, which has a width of W, and we want to know how much charge is there inside that box. So we know that the sheet, entire sheet, has a charge density of rho. So that means the total charge must be a multiplication of rho and the surface which is inside that box. So the surface inside the box is just a multiplication of W and L, and I multiply it with the charge density rho to get the total amount of charge inside that box. So just brush it out. Find out the value of electric field. You cancel W and L. I'm sorry. Instead of H, I should write L. Sorry for the confusion. So you just cancel out all these terms from the left hand side and right hand side, and eventually you will get to the following. Electric field is simply a proportion of rho over 2 epsilon. Okay? That's the final expression of electric field. Everyone taken the note? Okay, good. Now let's see. This is the math part. And as I always say, that math is important, but more important part is to understand and compare. You compare with what you have learned previously. So previously we learned that for a long piece of wire, electric field is equal to 2k rho divided by probably G. Right? For a point charge, our electric field is K rho or KQ divided by D square. And for sheet of charge, electric field is rho over twice epsilon. Did you notice something interesting in these three equations? So one is for point charge, one is for long wire, and one is for a long piece of sheet of charge. Okay? Did you notice that how this electric field depends on the distance d? So for the first guy, for point charge, electric field is inversely proportional to the square of d, right? Inverse correlation of the d. D is the distance from the charge. From a long wire, for a long wire, electric field is proportional to just 1 over d. It was 1 over d square, it is 1 over d. How about this guy? What is this relation with the distance d? There is no relation. Isn't it a wow factor? What? That's crazy. Absolutely, that should be the expression. That's crazy, and you may say that I don't believe it. It's impossible. We do know that if you take a point, go away from the source, of course the impact is going to reduce. But this guy is saying that no matter where you go, the impact is not going to change at all. How come? Do you follow that why it's a point of surprise? Why it defies our common sense? That how come if you take your point further and further away, you have the same electric field everywhere. So, in order to understand it, let's see that if we can draw a picture and explain something. Let us only start with a piece of wire, long piece of wire, and then we'll go back to this sheet. So for a piece of wire that carries a charge density of rho, if I try to calculate electric field at a point P, at a distance d from the long piece of wire, we know that all these segments would have some contributions to the total electric field. Let's say this is E1, this is E2, so on and so forth. Right? Now, tell me the following. For this picture, I drew a small piece of segment come to mirror position of this long wire, right? And I know that the contributions is going to be adding up in the x-axis, but they are going to be cancelled along the y-axis, right? So if I ask you this question, what if instead of here, I take my point P up there, I increase the distance d. What would happen to the contributions of the small mirror segments? These small segments would now have a new vector along these directions and along these directions. Right? The question is whether the contributions has increased or decreased.
Decreased.
Decreased. Why you think that the contribution has decreased? If I shift my point P further away, why you think the contribution would decrease? D is decreased. Fine. Does anybody think otherwise? No? I think very carefully. If you think in this way, if you take this point P, take this point very close to this surface, to this wire. Let's make it really, really close to this wire. What would be the contributions from these two mirror guides?
Very little.
Why very little? I came very close. Why is very little?
Because most of their forces cancel out.
Absolutely. Absolutely. That's the answer. Does everyone follow?
Yes.
If I take this value P, take this point P, come very close to each other, look at the corresponding contributions from these two mirror guides. One guy is having an electric field along this direction, almost perpendicular. And the other guy, we also have a perpendicular contribution of electric field. Do you notice that they almost cancel out each other? Because they are almost perpendicular, very close to each other. So, it's not easy to say that if you take the point P further and further away, you would have lesser and lesser contributions. It was true only for a point source. If it is a point source, then the case is very simple. The further you go, the smaller the contributions, not a problem at all. But for other geometries, not that simple. You just showed it here. That if you take the point P very close, these segments would have very little contributions because they are going to cancel out each other's impact. Right? So, when I asked you back previously that what happens when I take P further away and I ask you what is the contribution of this guy, you should take care of two important things. One is the distance, of course distance matters, and the second thing is because it is mirrored and they are cancelling out their y component, how much y component is being cancelled out? The further you go, the lesser y component is going to cancel out. Okay? If you come closer, more y component is going to cancel out. So it's not easy to say that whether if you go further away from a wire, whether those mirror segments would have a smaller contributions or a bigger contributions. Actually, there is an optimum point beyond which you will have a smaller contributions, and on the other side of that optimum point, you would have stronger contributions. Okay? So a lot of things actually play around, and why it's like that is only because these are vector fields, and vector fields makes things much more complex but interesting. Okay? So in the following class, we will use the same argument, and we'll try to see that why, if you have a very long piece of sheet of wire, you essentially have no dependence of the separations or of the distance of the point from that sheet of charge. Okay? All right, thank you guys. Thank you for your attention. So we will see you next week.